Hi everybody. This is the lecture overview lecture to go along with lesson 7 or assignment 17. This is probably one of the more important sections in the whole book because we're actually going to put the stuff that we've been learning about calculus and optimization to use. So you're going to get to see optimization applied in a couple of different scenarios. So I want to start you off with a joke, which is only, well, it's relatively funny for a math joke. Okay, so it's a physicist, an engineer, and a mathematician are given the same challenge. They get 20 feet of flexible fencing material, and their challenge is to enclose as much area as possible using that 20 feet. So the engineer goes first, and he knows that amongst all possible rectangles, a square has this property that it contains the greatest possible area for a given perimeter. So he makes a square fenced region. And let's see, I guess it would be about 5 feet on a side because 4 sides, 4 times 5 is 20. And so he gets 25 square feet of area inside of it. It's pretty good, I guess. The physicist, though, he knows something a little smarter. He knows that a circle is the figure that has the most area given its perimeter period. So he makes the 20 feet into a circular fence, and that will, trust me, have a little more than 25 square feet in it. Not a whole lot more, but it does better. So the mathematician goes last, and he just cuts off about 4 feet of material and wraps it around himself like a skirt. And the other guys are laughing at him like, "You idiot, that's way less than what we did." And he says, "No, you're mistaken. I'm on the outside." Okay, so why did I tell you that joke? Not really for the humor capacity, but because it illustrates a feature of these optimization problems that you should look for, and half the job is in recognizing these items. There's always an objective and a constraint. Almost always an objective and a constraint in these problems. Sometimes there's multiple constraints. But the objective is the thing you're trying to find the best value of. Either if it's, sometimes the best value is the largest. Other times the best value is the smallest. In the joke, we were trying to maximize the area of the region enclosed by the fencing. So you were trying to maximize, find the biggest value. If the problem involves, the expenses for a business, then you're probably looking to get the minimum value, right? So depending on the scenario, either biggest or smallest. So that's one feature, the objective function. What are you trying to find the best value of? The other feature, the constraint, is something that prevents you from just going hog wild. In the joke, the constraint is they only have 20 feet worth of fence to work with. If you had an unlimited amount of fencing, you could make the thing as big as possible. Of course, with the thinking outside the box approach that the math guy does at the end, you only needed a small amount. But still, that's a common feature. Objective and a constraining condition that prevents you from just making the objective infinite. All right, so let's do a real example. A little bit unusual, but this is a chunk of sheet metal that I've, it's aluminum. It's fairly flexible stuff. One, you may notice there's like red letters on it. That's because there's a protective sheet of plastic on this stuff, and I'll peel that off when we're done. But it allows you to write on it and then peel it away when you're finished forming the object you want to form, so that you don't have writing on your finished part. So the way I've got this laid out, I'm using solid lines for places where I'm going to cut, and dashed lines for places where I'm going to bend. And so what we're doing here is we're going to cut out these little square notches in the corners, and then we're going to bend the remaining tabs upward. Well, actually, I think in truth I'm going to bend them downward because that's easier to make the apply the force that way. All right, so I'm doing this live. I'm not sure how well it'll work, but I have these HVAC shears, and I'm going to put them on here and try to cut out the notches. Well, that actually worked pretty well. I'm going to pause and go ahead and cut out all the notches because there's really no reason for you to sit here and watch me fiddling with this. All right, so there we go. Oh, last one didn't fall off. So there we go. We've got the thing with the notches removed in the corners. And I just want to point out, it's kind of important that these parts that we removed were squares, because when we bend the sides up, we want this side and this side to come up to the same height. So the dimension here and the dimension here have to be the same in order for that to happen. So the next thing, ideally you would have a thing that's called a sheet metal brake for bending things like this. I have a lot of tools, but I don't have one of those. So I have these things that are meant for doing small bends, and I'm not sure how well this is going to go, but let's give it a try. Kind of clamp them on, and that could have been worse. So we gotta, usually you try to over bend it and then straighten it out a little bit. It looks pretty decent, I'm thinking. You see what I've created there? Trying to figure out what way is it best to show you the thing. All right, let's try that on the other side. The ones I'm actually worried about are the long sides. Those are going to be tougher to bend because there's more length of metal that's needing to be bent. Okay, that wasn't so bad. Again, I bent it a little beyond where it needed to go and then pulled it back. Okay. There's the tough ones. I could have been worse. I'm going to try moving them around a little bit. You heard a clunk sound just now. That was the metal skipping past the edge of the other one that was bent up. So it's pretty decent. I'm not going to be too anal retentive about this because it really is just here for a sample. But let's get the last side, and then the final step in making a box like this would be to use something to seal the corners up. A typical thing would be to put a little bead of weld on there, but I'm not going to bust out the welder and do that now. So I am trying to get it to bend so that the sides actually touch each other. It's slightly a challenge, but, and you can, if you look at this closely, you can see some flaws that I was working quickly. See how this side is a little taller than that side? That wouldn't be good. We'd have to come back and use the shears to take that away. But these edges now have come in close enough to one another that you could weld that together and make a solid box out of this. All right, well, why am I showing you this little metalworking example? Well, we've made a box that has a certain volume, and it's very common that you want to maximize the volume. You've got a certain amount of material to use. How can you make a box that has the largest capacity given that amount of material? Well, what it depends on is how big those squares are. These squares that I cut out, these were about 1 inch on a side. What if I had made them bigger? If I'd made them bigger, the box would be taller. But it would also not be as wide or as long. So we'd reduce the length and the width, but we'd increase the height. There's a couple of extreme points you can think about. What if these things were minuscule? If I only made them like 1/8 of an inch big? The box would be much wider, much longer, but it would have hardly any height, any depth. And so its volume would be quite small. The opposite side of that is I could make them almost as big as possible. If I made them really large, well, this end would be almost size 0. In fact, I guess you could think about the extreme cases. You make the notches big enough that the notches run into one another, and you don't have anything to use for the flap that bends up on the end. So, yeah, our job is to figure out the value of that size of the notch that gets the box with the maximum volume. The constraining conditions here are in the amount of material we began with. What was the size of the thing to begin with? the material I started off with was 5 inches by 7 inches. I'm just going to make a picture of a rectangular piece of sheet metal. This was 7 inches wide, 5 inches in the other dimension. And the pieces we cut out, those we're going to call them X by X pieces. They're on the corners here. So this part is gone, right? We won't have that anymore. Same on the other end. That's removed, that's removed. So how long and how wide is the box? Well, the width of the box is actually the dimension from where we folded the metal to the other side where we folded the metal. In other words, this length from here to here. And that's no longer 7 because we brought it in X from this side and also X from that side. So this guy, this dimension is actually 7 minus 2X. And in the other direction, remember where the fold lines were, lined up with the notches, that the dimension is going to be 5 minus 2x for similar reasons. So when we finish folding up the box, we're going to have a solid region there whose dimensions are, let's call it B for volume. 7 minus 2x is one dimension. 5 minus 2x is the other dimension. And x. You know, x is how tall the box will end up being. So x is the third dimension of it. Well, that's a thing that you can work with now. You've got an expression for the volume as a function of the size of the notch. And that's going to allow you to, differentiate. Figure out where you've got a horizontal tangent. You can look at this thing just from, the 1,000-yard look at it. It's going to be a cubic. And it's going to be a cubic with the coefficient of x cubed is going to be 4, because there's the term, all the terms that involve x have a minus 2, a minus 2, and an x, or a 1x. So let's turn to GeoGebra and expand that so we don't have to do it by hand. All right, so I'm going to ask for the expansion. So the command is expand, and then just plug in the things that I just had. So that was 7 minus 2 times x times 5 minus 2 times x times x by itself, and parenthesis. See what it does. Oh, there you go. It's 4x cubed minus 24x squared plus 35x. There's no constant term. That actually makes sense because there was a factor of x in the things that got expanded. And wow, you can see what the graph is like. It's a kind of typical of a cubic graph. It goes up and down, has a sort of an S-curve in it. Now, interestingly, there's places where the volume is negative, right in here, and there's places where the volume goes to infinity, over here, and even to negative infinity on the left. That's pretty strange behavior, and it's because there is only a small possibilities for the value of x. The equation we've got there, its default domain would be everything from minus infinity to infinity. But that is not really the right thing for this setting, this physical setting. Could x be a negative number? No, it's the size of a notch we were cutting out of a hunk of metal. So, it's never going to be negative. And could x be big enough that we get into this regime where we have, well, on the one hand, negative values, or on the other hand, really gigantic values? Again, no. The biggest x could be is we could cut out till we got to the halfway point, the midpoint of the smaller dimension on the box, which would be, or on the sheet metal, which is 2.5 inches. So really what we have is something whose domain should be restricted between 0 and 2.5. And I think you'll notice that those are the spots here and here. where it crosses the axis. In both of those, if the notch has 0 size, you're not going to get any volume because the box doesn't have any height to it. And if the notch is 2.5 inches, you're not going to get any volume because it's nice and tall, but it has got no width at all. All right, so this is really the right place to do, and GeoGebra has actually found the max for us. It's right there. The extremum is at well, the x-coordinate is 0.959. That means my box here was really pretty close to the right thing, because the notches there were 1 inch. 0.9, a little bit smaller notches would have been slightly better. Yeah, interesting. I just eyeballed that, what would make a nice box, but I kind of got it close to being right. It's kind of funny how often the human eye is good at that kind of thing, just guesstimating what would be the optimal solution. It's sort of evidence that evolution has endowed with our brains with a little bit of calculus ability. All right, so let's go ahead and do the calculus. I'm going to switch the view back to where we can draw. And what we had was we found the expanded form of this was 4x cubed minus 24x squared and plus 35x. So let's take the derivative of it. V prime is going to be, well, it'll be 12x squared minus 48x plus 35. So when is that equal to 0? Because that's where we'll have our horizontal tangents on the graph of the volume, and that means we're at a peak or a valley. But in the case of the part we're looking at, on the domain we're looking at, it's really just there's only one extreme value, and that's a peak. That's a maximum. I guess I want to turn back to GeoGebra for us to find that. I just returned to the GeoGebra window, and I replaced the command that said expand right here with the one that says derivative. And so we took the derivative of the thing, and it's plotted it for us. Of course, we could do the derivative of this one by hand, but I thought it would be just easier to get the computer to do the work for us. Now, again, we have this range from 0 to 2.5 that we're concerned with. There's 2 zeros, but one of them is outside that range, and the other is right there. And remember that number we saw before, where the maximum occurred? Around 0.96, and that's it. That's the 0 of our derivative, which is a critical number, and in the end it turns out to be a maximum for the function. It's a local maximum if you think about the function as being defined on the entire real line. It's a global maximum if you restrict the domain to the parts that are physically meaningful between 0 and 2.5. Well, that was one example of a applied optimization problem, and there are others. So I want to show you next a category of things that come from some sort of a farming perspective. So not business applications yet, but they're I think people call them pen problems. They're problems involving creating corrals to hold animals. The simplest one that I know of is something like this. There's some sort of natural obstacle, maybe a cliff or body of water, or the edge of a building, and we're building a enclosure for animals that sticks out from that natural obstacle. So the idea then is that you don't need fencing on one side, but on the other 3 sides you do. Let's say that the dimension out from the obstacle, whatever it is x, and the other dimension is y. So the area of this pen that we're creating is easy. It's the product of length and width. It's a rectangle, right? So A is xy. That's our objective function. We want to find the way of setting up this enclosure so that the animals get the most room to move around in. I mean, if they're grazing animals, this is them getting the most access to food. So that's a good thing generally. The problem, though, is how are we going to do calculus here? I'd like to take the derivative of A, and I've got two variables in it. Choice, which do I take the derivative with respect to x or with respect to y? And either one is going to leave variables in the result, so no, that's not good. What we need is a constraint. And I didn't say it ahead of time, but you don't have an infinite amount of fence to use to make these three things. They're cost limits on what you're willing to spend on creating an enclosure for your pigs or your goats or whatever. So let's say the amount of fencing available is, say, 100 feet. So this is our constraining condition, and it'll let us write an equation that that we can use to further solve the problem. The amount of material used in this thing in the abstract is you've got two pieces of length x and one piece of length y. So that is the constraint that we can work with. 100 equals 2x plus y. So the pattern on this kind of stuff is going to be very consistent. Once you've found a constraint condition, you'll solve it for one of the variables, and you use that solved constraint to eliminate a variable from your objective function. In this case, look at that sucker. Y is the easy one to solve for, so let's do that. Y is 100 minus 2x, right? And that means the A up here can now be turned into A equals x times y, but y is 100 minus 2x. Great. We could use the product rule, or this one's not at all hard. I'm not even going to turn to the computer to expand it. We get 100x minus 2x squared. Well, this feels cheap, but I'm going to save a little paper and write here on the next side. What's the derivative of that? 100 minus 4x. I can almost solve that in my head, because this is equal to, it's not solving that, it's setting that equal to 0 and solving that. All right, so here's our condition for finding the critical point. Set the derivative equal to 0. And now what do? Well, yeah, do you see that x equals 25 is going to be the answer here? 4 times 25 would be 100, and then 100 minus 100 would be 0. So you can just spot the solution there, x equals 25. And it's unique in this case. X equals 25 is our answer. Well, then what's y? You can go back to your constraining condition. In fact, go back to this version of it, which was solved for y, and let that tell you what y is going to be. 100 minus 2 times x. X is 25. That makes that a 50 here. So, oh yeah, y is 50. Does that make sense? Those two things together, two of the x's and a y, get you a total of 100. So that one way to think about these problems, these pen problems, is that there's a balance between the length that you use in one direction and the length that you use in the other direction. You see that in total, we've used 50 feet for horizontal, and we've used 50 feet, 2 times 25, for the vertical. That balancing condition is actually a quick way to answer a lot of these questions. Let's proceed to do one more of these silly pen problems, and then we'll get into the real finance type issues. So this example, also not terribly hard to get through, but may feel a little artificial. A farmer, I suppose, wants to make a pen in this shape where it's got two rectangular corrals that are adjacent to one another. I suppose it might be the case that you'd want to make pens, but you for some reason don't want the animals to mix. Yeah, I could picture that happening. Like, you know, if you have geese and ducks and that kind of animal in here, and you have goats and pigs over here, maybe the goats would bother the geese, so you don't want to have them get mixed up. So we've got a big region to enclose, but then a central divider to put in. The individual pens are going to be X by Y, so we're going to maximize the area. Now, really, you might like to say you're maximizing the total area of the thing, which would be 2x times y. But if you make this biggest, you'll also make that biggest. Okay, so it's fine to just use a equals xy. In fact, there's a calculus way to think about that. If you have xy and you have 2xy, they differ by a constant multiple. So their derivatives will differ by a constant multiple. And that means their derivatives will have the same zeros, right? So wherever one's 0, the other will be 0. Something times 0, but still 0. So, yeah. So it's fine to just work with a equals xy here. But our constraining condition is going to be more interesting now. There's a total of 4 pieces of fence that are x units long, and there's 3 pieces that are y units long. Now, if I have, say, 60 feet of fence to work with, here's the constraining condition. 60 would be 4x plus 3y. Okay? So the program that we're trying to do is to maximize the area. It's kind of nice there's a sort of standard form to set up what you're doing for an optimization problem. Tell us what you're doing. Is it maximizing or minimizing? Tell us what function or what variable, what quantity you're trying to find the maximum and minimum of. And then name the constraint. And usually we say subject to. So that's a nice formalized way to describe the problem we're after. You should maximize xy subject to the constraint that 60 is 4x plus 3y. Now that constraint is less easy to solve for one of the variables, but you know, you can do it. I generally, if it's a toss-up which one is easier to solve for, I'll solve for y, just because. So let's see, we'd have 60 minus 4x equals 3y by subtracting 4x from each side, and then just divide by 3. Maybe I can just do that now. So I'll solve that 3. So y is 60 minus 4x over 3. That means our area function is x times y, which we just found, which is a fraction. Now, let's go ahead and multiply the x in. You know, if you have something that doesn't look like a fraction multiplied by something that does look like a fraction, just turn the other one into something over 1 so that it now looks like a fraction. Yeah, and then you can multiply tops and bottoms. So you get 60x minus 4x squared over 3. So the constant multiple rule actually lets us know that it's kind of pointless to have this dividing by 3. That's just a constant that we're seeing in the function, and that'll turn into a constant in its derivative. So it's fine to just ignore that over 3 if you like. One thing I really want to point out is some people are tempted to use the quotient rule at this point. And that you don't want to do, because that's not a function in the bottom of the fraction. That's just a number. So you can, if you like, you might pull the over 3 out as a 1/3 up front, and then 60x minus 4x squared is the real meat of the area function. All right, so what's a prime going to be? Again, it has this 1/3 factor that comes along for the ride when you have a constant multiple. The derivative of 60x is 60, and the derivative of 4x squared is 8x. So where is that 0? Well, we just are. I'm kind of running out of space. I'm gonna. Oh, I see. I did some badness there, didn't I? Worked off the bottom of the screen for a second. How far off the bottom of the screen was I? I think I still probably had this on, where we multiplied the x into the 60 minus 4x over 3. Here's the pulling out the 1/3 and then taking the derivative. So where is a prime equal to 0? The derivative is 0 when 8x is equal to 60. Right? Because anytime you have a subtraction thing and you're saying when it's 0, you just set the two parts equal to each other. That's kind of a easy shortcut. So x is 60 over 8. I guess I wish I had started with 80 feet of fencing instead of that. 60 over 8, I think that's 7.5. Yeah, 7.5. So we have 7.5 feet here, 7.5 feet here, and then how long is y going to be? I mean, the way I drew it, y would have been like 3 times as long as x. Where do we figure y out? Yeah, see, back at this stage we had a constraint solved for y. So you just need to plug 7.5 into the x right there. 4 times 7.5 is 30. 60 minus 30 is 30. 30 over 3 is 10. So y is equal to 10. I did that really quickly, but that was just mental arithmetic. You could certainly stick that into a calculator if it bothered you. So x is 7.5, y is 10. Now I can't help pointing out the balance condition here. If you wanted to solve this more quickly, you'd say use half the available fencing for the vertical pieces, and half of 60 is 30. So that means each of those y's is 10. That's what we got. And then half of the material, the remaining 30, would be used for the other direction, the horizontal ones. There's 4 lengths of size x, and 30 divided by 4 is 7.5. So again, the balance condition gets us the answer a bit more quickly. But you know, you can do the point here was really to give you a simple model of doing an optimization problem, and I think that is you know, it's simple, but it's not trivial, right? There's some work that goes into that. All right, we're going to end today's session with a quick example of something that's more in the financial realm, as I think that'll help people to feel like this stuff is really applicable. This is example 2 out of the text. I just want to read it through with you, and then we'll solve it. So we've got a concert promoter who is selling concert tickets for $50 each, and at that price she finds she can sell 1,200 tickets. But an additional bit of information is that if she raises the price by $5, she finds that 50 fewer people will attend. So the question then is to figure out what price should she set in order to maximize revenue. Now, one thing to notice is that by changing the price to $55, you change the number of tickets sold to, instead of 1,200, it'd be 1,150. But 55 times 1,150 is a larger number than 50 times 1,200. In other words, you made more money even though you sold fewer tickets, because the tickets you sold at a higher price. So it's not unreasonable to raise this price some. So don't fill the hall necessarily, but make more money per ticket. So the revenue in this case is really easy. The formula for it is the price times the number sold. P is the price, Q is the quantity of tickets sold. So R is P times Q. Now, that's the thing we want to maximize, right? Revenue. Yeah, the initial question in here was, what price should she sell the tickets at to maximize her revenue? So that phrasing tells you you're a maximization problem, and revenue is the thing you're after. Um, but unfortunately, revenue is stated in terms of two variables. We need to have some kind of condition that will let us reduce the number of variables. So let's transition over to where I can draw. Okay, so we've got this. R is P times Q. And that's the thing that we would like to maximize. So we want its derivative. The problem is that we've got too many variables. All right, so how do we figure out something that will let us reduce the number of variables? It comes from that information we had about, if you raise the price a little bit, it'll reduce the number of tickets. So let's make a crude graph here. We had that at $50 we sold 1,200 tickets. So that would be 50 on the x-axis, 1,200 was the y-axis. At this point, 50, 1,200. Right? And we also found that if you moved over $5, I'm exaggerating that, but that would be 55, the number of attendees is going to drop by 50 people. So this guy has coordinates 55 and 1150. And the presumption is that that relationship is going to remain linear. That is, you will see a straight line that goes through those points. So we can calculate that. That's not bad. 50, 1,200 is a point on the line. What's the slope of this line going to be? Well, the change in y was we dropped by 50. For a change in x, that was we increased the price by 5. The ratio of delta y over delta x is -10. So that's our slope. M is -10. So then that makes the point slope form of this line be y minus 1,200 equals -10 times x minus 50. We might want to add the 1,200. Let's do a little algebra to simplify this and get it into the mx plus b form. Well, first, I'm going to leave the left-hand side alone, but let's multiply through that -10 through everything. So you get -10x, and then it'll become plus 500. And then finally, we're going to add the 1,200 to both sides. It's being subtracted right here. So final, what am I trying to say? Final form of this is -10x plus 5 and 12 is 1,700. Now, oh shoot, I've used y and x because that's what I'm used to, but these are really p and q. So which one is the price and which one is the quantity? Go back to our graph. 1,200 people, that was the number of people that were attending at a given price level. So it's this way. The x coordinate is really p, and the y coordinate is really q. So that is, in this form, what we really have is q is -10 times p plus 1,700. Well, we'll need to put that information together with our expression for the revenue, and I'm just going to write this on a fresh sheet of paper. Okay, so our new expression for revenue is the price times the quantity, but the quantity, that's, what was it again? -10 times p plus 1,700. And of course, that's a that's an expression that only involves p. So if you want to emphasize that, you can write this as r is a function of p, which is equal to, let's multiply through and make it a little simpler, minus 10 times p squared plus 1700 times p. Okay, now we're in a great spot. We've got our revenue is purely as a function of one variable, and we can do the calculus stuff. That is, find the derivative, and that would be, let's see, minus 20p. That p squared becomes 2p, but then there's a minus 10 out front, and that just becomes a number, plus 1700. So when is r prime equal to 0? Well, it's when 20 times p is equal to 1700. Just recognizing that's the term that's being subtracted, but this is really a subtraction. And so when the difference is 0, that means the two parts are equal. Okay, so, well, that's great. Then you just divide by 20. So p is, I can't divide 17 by 2. Oh, yes, I can. It's a 8.5, and then there's going to be zeros. I think it's 85. The question was it 8.5 or 850? Well, I'm not going to have a price of $850 for concert tickets. I suppose those do exist, right, for really headliner type shows, but we started at 50, so I knew I was going to be in the vicinity of 50. Almost didn't need to actually do the division. Here, you can take off a 0 on each side, and then it's 170 divided by 2. That's 85. Okay, so yeah, we found the price that maximizes our revenue, and since this is probably going to be reducing our costs as well, this might be a good thing. The real world situation might be slightly different. For instance, having lower attendance might be bad because it means you get less sales at concessions and, the t-shirts and the drinks and snacks and stuff like that. But, well, anyway, that's a pretty decent example of a real world application of calculus ideas to make more money, which is something that's good. Okay, we'll call it a day right there. Have a good rest of yours.